And welcome back. As we continue our cosmic journey, let's go ahead and take a moment to look at our expanding universe. First thing to look at is Slipher's pioneering observations. Curiously, the discovery of the expansion of the universe began with the search for Martians and other solar systems. This actually began back in 1894 with Percival Lowell establishing an observatory in Flagstaff, Arizona in order to study the planets and search for life in the universe. Now, Lowell thought that the spiral nebulae might actually be solar systems in the process of formation. He therefore asked one of the observatory's young astronomers to photograph the spectra of some of these spiral nebulae to see if their spectral lines might show chemical compositions like those that we would expect for newly forming planets. Now, the Lowell Observatory's major instrument was a 24-inch refracting telescope, which was not at all well suited to observations of faint spiral nebulae, especially as we know today. With the technology they had available in those days, photographic plates had to expose anywhere from about 20 to 40 hours in order to produce a good spectrum. This often meant continuing to expose the same photograph over several nights. And beginning in 1912, Slipher managed to photograph the spectra of more than 40 of the spiral nebulae, which of course would all turn out eventually to be discovered as galaxies. Now, to his surprise, the spectral lines of most galaxies showed an astonishing redshift. And when we're talking about redshift, this is just like what we expected from our earlier discussions on Doppler, but we mean that the lines in the spectra are displaced towards the longer wavelengths, in other words, going toward the red end of the visible spectrum. Now, if you remember, we have talked that a redshift is seen when the source of the waves is moving away from us. If it was a blue shift, then it would mean things are moving toward us. Now, these observations show that most spirals are racing away from us at huge speeds. In fact, the highest velocity that was measured was about 1,800 kilometers per second. In fact, only a few spirals, such as the Andromeda Galaxy, were actually observed to be moving toward us. And so that's going to get us down to a conversation about Hubble's law. If you recall, Hubble was a very important astronomer, and he had found many different ways to improve the accuracy of the estimates of distances to spiral galaxies. And he was able to measure much fainter and more distant galaxies than Slipher could hope to observe with his much smaller telescope. When Hubble laid his own distance estimates next to the measurements of the recession velocities, the speed in which galaxies are moving away, he found something rather stunning: that there was a relationship between distance and the velocity for galaxies. Basically, the relationship boiled down to this: the more distant the galaxy, the faster it was receding away from us. And so we can actually see this in the data. In fact, if we look at image A here, this is the data from Hubble's original velocity-distance relation, adapted from his 1929 paper in the Proceedings of the National Academy of Sciences. The second graph is showing data between Hubble and Humasson's velocity-distance relation, adapted from their 1931 paper in the Astrophysical Journal. Now, the red dots, of course, are indicating those original data points, and we can see them present in both of those findings. And the comparison really shows how rapidly the determination of galactic distances and redshifts have progressed. Now, we know that this relationship holds for every galaxy except for a few of the nearest ones. Nearly all the galaxies that are approaching us turn out to be part of the Milky Way's own kind of local group of galaxies, which have their own individual motions. Now, if we write Hubble's law out as a formula, we can map this relationship between velocity and distance as v equals h times d, where v is the velocity, d is the distance, and h is the number referred to as the Hubble constant. This equation as a whole is what we refer to as Hubble's law. Now, there are variations of the Hubble constant. The use of redshift is potentially a very important technique for determining distances because most of our methods for determining galaxy distances are limited to approximately the nearest few 100 million light years. Now, the use of Hubble's law as a distance indicator requires only a spectrum of a galaxy and a measurement of the Doppler shift. With large telescopes and modern spectrographs, these spectra can be taken of extremely faint galaxies. And this technique works if and only if the Hubble constant has been truly constant throughout the entire life of the universe. Now, A key thing to keep in mind is that when we observe galaxies billions of light years away, we are seeing them as if they were billions of years ago. We're looking into the past effectively. So a question you might wonder is, what if the Hubble constant that we've been talking about was different billions of years ago? Now, before 1998, astronomers thought that, although the universe is expanding, that the expansion should be slowing down, more decelerating, because the overall gravitational pull of all matter in the universe would have a dominant measurable effect. Now, if the expansion is decelerating, then the Hubble constant should be decreasing over time. But once we got the discovery of type 1a supernova, and we've established that these are standard bulbs, it gave astronomers the tools that were needed to really observe extremely distant galaxies and measure the rate of expansion billions of years ago. The results that astronomers found were completely unexpected. It turned out that the expansion of the universe was not decelerating, but instead was accelerating over time. And what makes this result so astounding is that there's no way that existing physical theories can account for these observations. While a decelerating universe could easily be explained by gravity, there was no force or property in the universe known to astronomers that could really account for this acceleration. So what are our choice models for an expanding universe? First thing you might wonder is well, are all the galaxies really moving away from us? Is there, after all, something special about our position in the universe? It's kind of going back to that mindset of the Earth. We talked about the Earth was maybe the center of our solar system. And come to find out, nope, it was the sun. And then we're like, well, maybe the Earth is in the center of the Milky Way. Well, comes to find out, we are out in the spiral arms. The fact that galaxies are receding from us, and that more distant galaxies are moving away even more rapidly than nearby ones, really just shows us one thing, and that the universe is expanding uniformly in all directions. A uniformly expanding universe is one that is expanding at the same rate everywhere. The expansion of the universe, by the way, does not imply that the individual galaxies and clusters of galaxies themselves are expanding. But what we find in such an expansive universe, that we and all other observers, no matter where they're located in time or space, must observe a proportionality between the velocities in distances of equally remote galaxies. This means that if I was an observer, let's say in the Milky Way, I'm going to see the universe expanding at the same rate as if I was an observer, for example, in the Andromeda galaxy, or even something that was in a different cluster of galaxies.